So hi everybody, thank you for attending today's session and joining me. And hopefully you find this session fruitful. First, I just want to say a huge thank you to the convention team staff and volunteers who put in the time and effort to putting the program together. It's my privilege to be able to share a few of my findings and hopefully you learn something as well. Greetings from Singapore. My name is Shiwei and I'm from the Singapore University of Technology and Design. In my lab, the thermal lab, we use material science as a starting point to study different natural systems and come up with engineering solutions to the problems that we face today. So in short, what we do in the lab is where we try to combine biology and material science together. So today's presentation on Martian Biolith, which is a composite that we devised for closed-loop manufacturing, is a research work that had been co-authored with Professor Javier and Professor Silianos, and who both unfortunately would not be able to join us today, but I will be representing that and sharing my results to you. Now let us start off with understanding the identified challenge, and that is how to achieve sustainable development on Mars. And while we are trying to do that on an alien planet, actually it's not a new challenge to us because on Earth we have been trying to move towards a sustainable development. And the reason for that is that right now we are experiencing symptoms of the climate crisis in different forms. And a part of that is contributed by our past inefficient use of resources, and which also embedded deep-rooted consumer habits that generally do not regard environmental impact as their primary consideration in products or services. On Mars, this challenge would be amplified, and it's actually the extreme test scenario of our ability to use local resource sustainably. Now, on deep space missions such as a prolonged crew mission or prolonged surface stay, long-term settlement, we will not be able to rely on space shuttling or space rockets to shuttle resources like food, water, oxygen to us because they are expensive and they are actually very vulnerable to external disruptions such as delay caused by weather and so on. So while on Earth logistical disruptions would actually just cause us inconvenience, this disruption when it comes down to relying on critical consumables would be a matter of life and death. Secondly, where we were to produce the consumables that we need on Mars, these resources are scarce, and everything on Mars is produced at an opportunity cost. As such, if we were to produce waste, that's actually akin to spilling water when we are in a drought and basically shooting ourselves in the foot, and that makes a tough problem even more difficult. And assuming that we're not trying to terraform Mars, right, some sort of planetary protection is required to ensure that the validity of scientific returns are protected. And this means that the waste that we produce has to be managed and, if possible, recycled and upcycled. Yeah. So while this might seem like a daunting task, it's actually not new in the sense that there are some places that can learn experiences have a clue of how to do it. At this point of time, there are a few lessons that we can learn from the International Space Station, which is right now the only sustained human presence outside Earth. Now, with an integrated closed system as shown on the left, we are able to regenerate much of the water and oxygen that we use, and waste are actually being contained. They're either being returned to Earth or burned up on re-entry. Now, if you see in this closed loop life support system, each building block is integrated and connected to each other, and humans are designed to be part of the system rather than just a consumer of the products. Now, in addition, we are also able to grow limited fresh produce on board the ISS through different projects such as Veggie Project and Advanced Plant Habitat Project. Now, these fresh produce are important not just as a psychological boost to the crew, but at the same time, they are also a lot more nutritious as they avoid the issue of prepackaged vitamin being degraded by radiation. Now, this means that as long as there are human crew and we need food, there will be other biological life supporting us. Now, building on these ideas of an integrated closed system and us requiring other biological form for food, uh, we can actually expand the idea of stewarding other type of life form for our life support system. And examples such as, besides the examples such as the Melissa project, which is a short form for microecological life support system alternative by the European Space Agency, microbes such as cyanobacteria have been proposed to fix CO2 from Martian atmosphere to transform them into food and oxygen that we need. Now, another way that life on Mars could be different is that cellular agriculture or lab-grown meat would be more common, and insects would be an alternative source of protein instead of relying on farm animals. Now, in a study by Kevin Cannon and team on what is actually required to feed 1 million people on Mars, insects were actually being proposed to supplement those protein, written protein requirements of Martian diet. And insect farming is actually a much lower maintenance solution that you require less space, less water, produces less greenhouse gases, and has a shorter production cycle. Now, I understand that most of, or some of us here are averse to eating insects, but the truth of the matter is that around 80% of the country on Earth and 2.5 billion people are already eating insects daily or in their meals. And the FAO, the Food and Agriculture Organization of the United Nations, actually suggested us to consider edible insect as future prospect for food and feed security. Volunteers from the China Lunar Palace 1 project actually had mealworms as occasional protein intakes. Now, recognizing that insects going to be part of this ecosystem, this brings us to the identified opportunity in our research work. And that is that though insects such as crickets are very high in protein, about 55% of their dry weight is just protein. There's actually a considerable amount of biopolymer, which is chitin, that cannot be digested by humans and have no nutritional value. Now, this would likely end up as a waste inside a closed-loop ecosystem. And hence, our idea is that instead of it being a waste resource or waste source, can we use chitin as a valuable resource for other manufacturing processes, or try to upscale the use of chitin into other products? Now, we know that on Earth, chitin is the second most abundant polysaccharide. Other than insects, it is found actually as a recurring component in different kingdoms, from crustaceans, algae, or even to fungi. It is a polymer that is similar to cellulose, except that one of its hydroxyl group, which is the OH group over there, is being replaced by an amine group, which is the NHOCH3. Now, another variant, chitosan, which is also naturally occurring, can also be found in nature, though they are in limited amount and usually found in fungi. Now, commercially, we use chitosan a lot more because it is soluble and easier to work with, unlike chitin, which is insoluble in water and regular organic solvents. Now, for chitosan, though we can harvest them from fungi, as I said previously, they are more often processed from chitin through a chemical process called deacetylation. Now, on Earth, what we have experience with is that chitosan can be used to fabricate functional objects such as cups, trays, and even certain chess pieces in injection molding. We can even mix them with other polymers such as cellulose and to form a composite called flames, a fungal-like adhesive material to 3D print a large tower over 5 meters. Now, knowing that we can do that, let us to narrow down our research question to whether we could implement similar strategies to using chitosan to manufacture things on Mars. And that is where we came to this idea of the Martian biolith. Now, in the next session, I'll go through very quickly the method and materials that we use in our work. Now, first off, for chitosan, as received commercially available chitosan is being bought off shelf, and we dissolve them in diluted acetic acid, which is about 1% in concentration, to get a final 3% chitosan solution. Now, this 3% chitosan solution is then mixed with Martian regolith. Now, as I mentioned before, chitin can be derived from different sources inside a closed system. Water can be derived from hydrated minerals or subsurface ice. And acetic acid, which is the simplest carboxylic acid, is actually a common byproduct in different fermentation process by different type of microbes. So it is kind of like a common resource that we anticipate being present on Mars. Now, for regolith simulant, we actually bought them from the Exolith lab, from the University of Central Florida, where they simulate composition, the particles distribution, and mineralogy of regolith scooped up by Curiosity from the rock nest area. Now, the idea of producing composite with chitin as a matrix and using inorganic component as a filler is actually pretty common in nature. And one of the example is nickel, or other known as mother of pearl, in which calcium carbonate is embedded in mortars made of protein and chitin. Now, our composite, which makes use of regolith and a biological component, is partly inspired by this idea, and hence the term Martian biolith. Now, with Martian biolith in hand, the following experiments were being conducted. Now, very quickly, first you want to understand how the material works on a micro scale and macro scale behavior and macro scale level. The reason for that is that the bulk behaviors of the composite in wet condition and dry condition most often is dependent on the micro scale and macro scale interactions. Now, after we understand the material on this level, we go on to 3 different applications that we sought to experiment with. Now, the first one is one of the oldest manufacturing technique, and one that actually require very low technological requirement, and that is casting. Now, this allows us to mass produce simple consumables or tools that we need on Mars. Second, since it can be casted, that means it can be manipulated in its wet form. So we wanted to try if we could use it in free-form application, where the only tools that you need are just plainly our hands, and we don't need any additional tools. Here we test to see if the material can be used to repair or join with other type of materials commonly used in space. Lastly, we tried to test this material in additive manufacturing application because the advances in additive manufacturing have allowed fabrication and construction to be done autonomously without any much interference or intervention for humans. And in additive manufacturing, it also allows us to have or implement flexibility in design, which allows us to reduce the amount of material being used. Now, all in all, the goal of all these tests is to demonstrate the potential application of Biolith in different application of increasing or different technological complexity in both fabrication and construction purposes. Now let's go to result. First off, the general bulk behaviors and mechanical properties of the composite. Now in its wet form, as we add in more chitosan, we can see that the workability of the mixture changes. In the extreme left-hand side, that is where we have a lot of chitosan solution and very little regolith. And on the extreme right-hand side, where there's a lot of regolith and very little chitosan. we see that the workability actually changes between the two extremes of being non-palatable and being very friable, which is very clumsy. The illustration at the bottom is just to illustrate or depict how the chitin solution is actually being dispersed, or the regolith particles is dispersed in the chitin matrix. Now, when it's dried, we actually took the samples and put it under scanning electron microscopy to just observe what is the structures that are being formed. And what we observe is that in the dried samples, the chitosan crystallizes, it shrinks, and then actually pulls in the particle together and seemingly entrapping them and physically agglomerating them together. Now, from this interaction or from this observation, we went on further to just investigate whether this interaction between chitosan and the regolith particles is based on a chemical reaction or physical interaction. And to do that, we actually perform two types of tests. One is the FTIR, which is the Fourier transform infrared spectroscopy, and the DSC, which is the differential scanning calorimetry. And these two tests, what we're trying to do is to compare the absorbance spectra and the heat flow patterns are measured as we increase the different temperature. So let me dive in a little bit more on the FTIR. So what we're trying to do in FTIR is basically measure the absorbance of different wavelengths by the different bonds on molecular level. The idea is that if there's a chemical interaction, the chemical bonds will be changed and hence absorb a different wavelength and present a different absorbance peak as compared to the original. In DSC, what we're trying to do here is that we're trying to measure the heat flow, and this heat flow is actually indicative of a change in phase. For example, when we know that when water evaporates, heat actually flows into the material, and there's a change of state or change of phase from liquid to gas, and hence it's an endothermic reaction. Now the idea here is that in DSC, if there's a chemical reaction between chitosan and regolith, we would observe some shifting in the peaks of the heat flow patterns here. So the idea is that if there's a chemical reaction, some of the mineral phases will be consumed or changed, and this altered mineral composition will likely have a different temperature at which they change phase. Now, looking at these two graphs on the left, which is the FTIR, and on the graph on the right, which is the DSC, we actually can observe that there is no distinctive change in the spectra between the Biolith components, which is regolith and chitosan, and the end product, which is Biolith. And this led us to kind of infer that there's actually no conclusive evidence that there is a chemical reaction that's happening between the components. Now, this means that the agglomeration is merely a physical interaction. Now, while physical agglomeration might be considerable, might let us to expect a lower mechanical strength, it could be an advantage because it also means that whenever there is variability in regolith harvested or Martian surface, the formation of biolith will not be affected by the chemical composition of Martian regolith, no matter where we settle at. And that is an advantage in of itself. Now, the next question that we're trying to answer is that in this Biolith composite, we want to minimize the amount of chitosan without compromising mechanical strength. And the reason for this is very simple. As mentioned before, everything is produced at opportunity cost, and hence chitosan being a product or being a resource that is metabolically expensive, we would like to reduce the amount of chitosan used. And for Martian regolith, where it is in abundance everywhere, we would like to maximize the use of the resource. Now, as we try to as we drag the composite in varying different ratios and subject them to mechanical tests, both flexural and compressive tests, what we find that is that uh, there is actually an optimal point or optimal range. Now, in these two graphs that you see over here, the horizontal bars between the group or co-relating two different groups actually signifies significant change or significant differences. So, okay, so let's go on with the graph on the left, looking at the flexural strength, which is the white color bar. As we add in more regolith, which means there is lesser chitosan, flexural strength actually increases until 1:75 or 1:100, where above which there is no significant differences. But however, if you were to add in more regolith, the composite is actually weaker in this test. For compressive strength, we realize that actually in the range of 100, 1:100 and 1:125, there is actually a significant drop. So that tells us that we should not increase the amount of regolith beyond 100 parts is to 1 part of chitosan. Now, from these two results, what we concluded is that for the subsequent tests, the optimal ratio without compromising on mechanical properties should be within the range of 1:75 and 1:100. And for the sake of workability, we focus on 1:75 for the rest of application. Now, it's worth noting that at the ratio of 1 gram chitosan to 75 grams of regolith, this is actually a very low binder content as compared to some of the literatures that I come across, and actually to a notable literature that I have reviewed that noted itself to be ultra low binder content. This 1:75 mixing ratio is actually half of that. Now, as you can see from the previous result, the mechanical strength is about 2.5 megapascal in terms of frictional strength. Now, how does that match up with the known materials? Just to put things into context. Now, we plotted this in SB plot, and we find that it's actually closer to being a brick rather than a concrete. And actually, the compressive strength is slightly lower than the brick. Well, one might argue that the strength is comparatively weak, but it's also worth noting that much of the material in this SB plot just do not exist on Mars. And in fact, we probably will need to come up with a new HP plot of materials that's available and performance and with known performance operating in a Martian environment. Now, let's move on to the application process, the application portion. First, in casting. So we try to cast a functional object, which in this case is a wrench, and we try to subject it to a downward force using a universal testing machine. And what we realize is that as we subject more and more of downward force on an already tightened nut, the wrench actually fails at about at the top above 2.75 Newton meters. And that is actually that is the minimum required torque for N5 bolt for non-critical application. Now, this is actually useful in the sense that for consumable tools that are easily damaged, we could actually replace them and cast them very quickly. And they do have a functional use as demonstrated in this case. Now, as in casting, another question that sort of follow up from this experiment is that whether there is significant shrinkage between the model and the cast object. So to do this, we cast a few objects of increasing complexity of curved surfaces and multiple grooves just to test out how much the material shrink before and after drying. And we compare them to the original model. And what we found that by comparing the volumetric scans is that there is a maximum of 3 mm deviation, surface deviation, and a 10% contraction in volume. Now, this would be useful information if we were to uh, design our future moves. Now, knowing that we can manipulate them in wet form, we move on to the next application, which is free-forming application. Now here, what we try to do is that we try to use Biolith in a wet state to plug in and cap a pipe that's leaking. Now in its wet state, the Biolith is able to adhere to the surface of the pipe with excess material actually entering into the pipe and forming sort of an anchor because of elastic deformation under gravity. Now, when this patch is dry, this actually forms an internal anchor that seals the external patch against the acrylic pipe, and this effectively seals and holds water within this pipe and repairing it in the process. Now, the follow-up question that we have is that since it can repair a water-containing device, what is the pressure at which this sort of repair could sustain or could be or withstand? And in this case, what we did was that we did a modified burst test where different discs with a pre-cut hole in the middle is being prepared, and we patched the hole with Biolith. And after drying, we actually subject it to increasing pressure, increasing hydraulic pressure in on-sitting and off-sitting condition. On-sitting means that the pressure is pushing the Biolith patch against the substrate, while off-sitting setting means that it's pushing the Biolith repair away from that substrate itself. And the result is this, that we see that they are actually able to sustain a pressure of at least 100 megapascal in off-sitting condition. And this is useful because this is actually higher than the atmospheric pressure that we have on Earth, or even in a lightly lander cabin pressure. This means that if we have water-containing volumes in these environments and they are leaking, we can actually use this material to patch them up, and they should be able to hold liquid in those volumes. Now, one very interesting observation here is that the aluminium, the repair on aluminum substrate seems to be a lot lower than the repair on PLA substrate. And that leads us to this question. Why is that so? Is that an interaction between the Biolith and a different type of substrate? So to do this, actually what we did was that we applied it as an adhesive and we tried to do a lab shear test. And what we can observe from this is that there basically isn't any difference between aluminum substrate and PLA substrate. But what else could be the reason for the difference in performance when sustaining hydraulic pressure previously? Now, our hypothesis or postulate is that these differences might be because of mismatch in stiffness between Biolith and the substrate itself. So an easy way to think about this is that if you have a very stiff substrate on which Biolith is being applied to, when there is a very high hydraulic pressure, the entire substrate, because it's very stiff as compared to Biolith, it would be less likely for the substrate to deform, and in turn, the hydraulic pressure would kind of cause an accumulation or concentration of stress at the repair site itself. And this causes rupture or burst failure to happen earlier. Now, finally, in additive manufacturing, what we did was that we realized this mixture in its wet form is actually a shear thinning material. And what shear thinning material means is that its viscosity actually reduces when we apply shear stress to it. And it's a very useful property because the ability to build and extrude material actually depends purely or depends heavily on the rheological property of mixture. Now, in a shear thinning mixture, when we apply shear stress to it, it would allow us to extrude the material with ease. Yet at the same time, once it's extruded, the shear stress is elevated. It actually retains its shape and allows subsequent layers to be added onto it. Now, we actually demonstrate it in this application by replicating a scale model of the Martian habitat, which is the winner of a NASA 3D printing competition. So we basically mounted a pneumatic drum extruder on a robotic arm. We drew a scale model in Grasshopper, converted into a toolpath for the robotic arm to follow, and then extruded out the material as you can see here. As it is being extruded, we accelerate the drying process using a hot air gun so that we can build we can build more layers upon it. So with these three different segments, we apply Biolith as a masonry to join these three different segments and form kind of a scale model in the context of mass, as you can see here. Now a magnified view as shown here is this, and this is where we could envision Biolith being a single material used in three different applications: 3D printing, and as a masonry to kind of join the segments together. And for the top, because it couldn't be 3D printed, we use actually a casted top. So this actually is a demonstration of three different applications: 3D printing, preforming, and casting. Now, in comparison with other proposed material, Biolith is actually a unique material in the sense that it is the only material that can be used in such a versatile application, both additive manufacturing and non-additive manufacturing methods. It also uses less energy because it does not require elevated pressure to compress the particle, or it also does not require elevated temperature to melt certain composition. Now, as compared to different materials being proposed in other literatures, it actually has equivalent technology readiness level, and it's actually built on known technologies. Now, to conclude this presentation, a closed-loop ecosystem encompassing chitosan and Biolith is actually being shown here. Chitin and chitosan could be extracted to derive from insect farming, or actually in another type of insect, which is black soldier fly, in the application of waste management. Now from there, the XUVs, which are a lot of time waste, but in our case, a valuable resource, can be used to produce chitosan and used in different applications other than what we've demonstrated, and into applications such as pharmaceutical, soil treatment or dust control, and even directly using them as bioplastics. To recycle them, we could very easily dissolve them again in 1% acetic acid or diluted acetic acid to retrieve chitosan solution and reuse them in other applications as well. So with this, I come to the end of my presentation, and I hope that this presentation has been fruitful to you. And if you have any questions, do let me know, and I'll try my best to answer them. Thank you for your time. Thank you.